Halides, alkyl halides, are really commonly used for the big four reactions. And so we use halides. What makes halides so good in the big four reaction is that we always need something that will leave. In the SN2 reaction, we have to kick out a leaving group, and that ends up being a halide. In the E2 elimination, we end up, as we make an alkene, we kick out a leaving group, and that again is the halide. In SN1 and E1 reactions, we need something to leave. And what makes halides so good is they're really stable anions. They don't put up much of a fight to get thrown off a molecule because they form these stable anions that are happy to live in solution on their own. Well, as it turns out, alcohols are super useful in big four reactions. But alcohols have a serious problem. Let's look at T-butanol. The problem with T-butanol is this OH group is not a leaving group. How do we know it's not a leaving group? Well, if OH leaves, and when it leaves it's going to take this pair of electrons, it's going to form OH minus. OH minus is unstable. Well, we see it a lot of places. Why do you say it's so unstable? Well, it's unstable because it's highly reactive. I mean, it's a strong base. So when things are reactive, they're unstable. Unlike bromide, no one would ever say that bromide's a strong base. It's a very stable anion. So alcohols have a problem. So if I want to say that alcohols are very useful for the big four reactions, then we need to have some kind of explanation of how do we convert an OH group into a leaving group. And there's one way. We're going to protonate our OH. So let's look at T-butanol. Let's treat it with a strong acid. I'd say for most of you, if I say strong acid, you say HCl. I'm kind of partial to sulfuric acid, but HCl totally works here. So we could protonate that oxygen with HCl, and HCl as a strong acid is more than willing to do that reaction. And we get to here. So now what we've done is we've gone from having an OH on the side of our molecule, which is a terrible leaving group, to having basically water. And when you see atoms that have a positive charge, I don't know if you speak atom, okay, but this atom is telling you, I've got a positive charge, I want electrons. And this bond, if it breaks, gives that oxygen the electrons it wants. And what does it leave? As it leaves as water. And that's about as stable a molecule as you can get as a leaving group. And what it leaves behind here is, in this case, we leave behind a carbocation. Now, so the fact is, water is a fantastic leaving group. And we can generate this leaving group and do the big four reactions on it. Now, I want to qualify this a little bit. If we look at our big four reactions, we've got the SN2, SN1, E2, E1. We can do all of these on alcohols except for the E2. Why can't we do the E2 reaction on alcohols? Because the first step that we need our alcohol to undergo is a protonation with acid. What do you need to do an E2 reaction? You need a reactive anion, which is going to act as a base. You can't have do a reaction that simultaneously depends on strong acids and strong bases. Incompatible. So when we talk about alcohols, we won't do all the big four, but we can do the SN2, the SN1, and the E1, no problem.